thanks again, everyone, for joining us today on this beautiful spring day here in West Central Indiana. And I hope the weather is nice where you are too. So this is our last in our series. And of course, you know, the reasons why we do this are to showcase what we're doing here at Purdue, to let people know what other people are doing, and to help us along and to advance the science, as they call, in terms of using data to help us manage our crops and livestock and forests and food science and all the things that we do in terms of data-driven agriculture here at Purdue. So yeah, there we go. So if you're interested in more than we've got a dense set of information for you today. I'll tell you that. A lot of information from our speakers. But if you're interested in more, which I typically am, there's the website to go. Our previous webinars are recorded, and you can get the link to the YouTube place on there. The UAV site is also very good, and a lot of information there. And then, of course, we appreciate the support of WIN, the Wabash Heartland Innovation Network. So like I said before, this is the last for this particular semester. We'll be back in the future, and we'll let you know when the next one will be. Won't be this summer, but it'll be probably in the fall. And if you've attended these before, you know how they work. So we would appreciate if you eventually you can make sure you're muted and turn off your camera. If you do have a question, I have no problem interrupting the speakers, and so we'll put your question in the chat, and if it's relevant to what they're talking about right then, we'll interrupt them. If not, we'll wait till the end. So again, at this point in time, we have a couple of presenters today, and John Evans is one of them. He'll be the second presenter. John is a Kentucky raised farm guy and did his PhD at the University of Nebraska. He's an assistant professor here at Purdue in the Department of Agricultural and Biological Engineering. And we're really glad to have John here today, and we're glad to have him on employed here at Purdue. Our speaker that's going to start things off today is Dave Cappelleri. And looking at a little at David's information. He has degrees from Villanova, which pretty good basketball school there. Dave, were you on the team?
Actually not, but
yeah, okay. And also University of Pennsylvania, Penn State. He's a mechanical engineer, and I guess the most important thing is that he started and manages the multi-scale robotics and automation lab. And so we're going to talk a lot about automation and robotics and all those topics. And so Dave, why don't you kick it off, and we'll hear from John in a little bit.
Great. Okay, I'm going to share my screen here. Okay. Look good, you guys?
Yep.
Okay, great. So good afternoon, everybody. It's my pleasure to talk to you today. I'm going to give a nice little overview of our new National Science Foundation.
Hey, Dave, it looks like you muted yourself.
I'm sorry, that was me. I was trying to mute myself. I mean, leave it to me to do something like that.
Okay, hold on. Let me try that again. Okay, I'll start over. So good afternoon, everyone. It's my pleasure today to talk to you about our new National Science Foundation funded Engineering and Research Center on the Internet of Things for Precision Ag. For those of you who are not familiar with the NSF Engineering Research Center program, I'll tell you, quote, that it supports convergent research and education and technology translation at U.S. universities that will lead to strong societal impact. So that's the goal or mission of these ERCs, as we call them. So it started in 1985, and since then they have funded about 75 different ERCs across the nation. And the NSF supports each center for up to 10 years of funding. So we're hoping to get 10 years of funding out of that here to focus on IoT for ag, is what they call it. So it's been a very successful program. It's launched over 200 spin-off companies, over 850 patents, and more than 13,000 degrees of bachelor's degrees, master's, doctoral degrees of students working in these different projects. And so we're excited to get started with this. Ours just started in September, so we've been ramping up. So I'm happy to share with you kind of our goals and our mission and some of the research that we're trying to carry out here. So the vision for our IoT for Ag Center is, we want to be able to ensure food, energy, and water security by working on precision ag technologies to increase the crop production, so increase the amount of food that we can produce while minimizing the amounts of resources required, that being energy, water, and chemicals. Right. So the kind of motivation, the population is growing very fast. There's competition for land. Increased demands on water and other resources, and on this goal for being more sustainable. So it's kind of the vision for our center. So our mission is to try to create and translate Internet of Things technologies for deploying agriculture, and also to train a workforce who is proficient at these technologies, so we can address these societal challenges of food, energy, and water security for today and for the future. And so this is kind of a picture of kind of what we hope or we think the farm of the future is going to be like. So this is going to be basically integrated systems in the farm. So we're going to have embedded sensors, instrumented vehicles, ground aerial drones, everything communicating together, trying to capture the microclimate, both spatially, temporally, and also compositionally, in order to map all the stresses that are going on in the field in order to predict what's going to happen, or so you can take the appropriate interventions in real time. And so by deploying these technologies, the USDA predicts that we can get an increase in $47 billion per year in value of the crops by implementing these precision ag technologies. And so why is the time right for this? Well, we have exponential growth in information technologies. There's lots and lots of data is now becoming available. Lots of new algorithms and data scientists now we can use these techniques to fuse the data and figure out what's going on. And then we can also then implement this into the field with these new agricultural technologies, which are also coming online. So this IoT for Ag Center is really a partnership between not only academia and the researchers here, we also have government partners, industrial partners, and innovation partners. And we have the research thrust, but we also have pillars on engineering workforce development, diversity, inclusion, and innovation ecosystem, try to get this system, all these technologies out. And so there's three main thrusts. We have agricultural sensor systems, communication and energy systems, and agricultural response systems. And so these are very diverse topics. We need lots of experts in order to execute and lead this research. And so this is a partnership between 4 universities. So University of Pennsylvania is the lead institution, and then you have Purdue, University of California, Merced, and University of Florida. And so these is a snapshot of different PIs in these different thrusts. And at Purdue, it's really nice collaboration between the College of Engineering and the College of Ag in order to work on these different areas. So on agricultural sensor systems thrusts, we have myself and Melba Crawford from Purdue, and also Tony Vine. And then the communications energy systems, we have Jim Krogmeyer and David Love, and they're from ECE and the College of Engineering. And then agricultural response systems, we have Melba again, and also then Dennis Buckmaster, co-leading or leading these areas. And so it really is an integrated system, all these thrusts working together in order to realize our goals. And so I'll just highlight a couple of the thrust areas and kind of the research directions for each of them now. So everything is rooted in plant and environmental science, and particularly in thrust 1. And so we have certain targets for the plants or certain characteristics that we want to identify. You can see here, growth indices, nutrient status, disease, different stresses, yield rates, and also environmental targets that we want to monitor. Properties of the soil, diseases, compaction levels, water, and weed levels. And so kind of the question is, with all these different variables, how do they affect crop yield and resilience? And then how do we sample these? Like at what time scales do we want to get these variables, and what spatial resolutions? Should we try to deploy technologies in order to get this information that we can then help predict crop yield and resilience? And so we have the agronomists kind of trying to understand these interactions of these different variables. And then we also have the people in Thrust 1 who are developing some of the sensor technologies in order to deploy, in order to read these variables. And so we have multi-mode sensor science and technology here. So you need to develop sensors for things that we can't just observe directly, right? So we need to figure out sensors for water temperature, from pathogens, pH, et cetera. So if we look at conventional sensor technologies right now, what you see here, they have limited power, right? They'll run out of energy, and limited placement. So they're about, let's say about 0.01 sensors per acre, and they cost about $1,000 per sensor per season. So with our technology, what we want to do is augment these or add new sensors, which we call sensor chaff. So basically a whole bunch of sensors which are zero or near power requirements. And we can have thousands of these sensors per acre. And we can do this at very low cost. So they cost between 1 cent and $1 per sensor per season. And so we have some novel technologies we're working on how to manufacture these. And we need to also then communicate this sensor information out to the farm and to a fleet of drones, aerial and ground robot drones, in order to monitor things. And so we have some novel wireless communication technology, which we can use to communicate this data. And we also have some pretty neat optical technology where we can design the sensors so that they will change or give off different optical signals or colors depending on what they're sensing. And we also can use that information then to pick that up from our fleet of drones. And then we need the communication to go back to the cloud and then to the farmers and agronomists to make the appropriate decisions. So we want to be able to have the autonomous fleet operating in the field. And so these are examples of some of these that we're going to be working on. So these are aerial drones, which you see here in this video, which can fly above or below the canopy. This is in an orchard, an orange orchard here. So it can map and autonomously come up with different waypoints where it needs to be able to go and navigate. We're also going to have ground drones as well. And one neat thing that we can do is we can do something that's called semantic mapping. So not only can we drive through the trees and the crops, we can actually identify and count different kinds of fruit. So here we're counting oranges. And so not only can you map it, can you recognize what it is and then log that information. And so then one notorious problem that you have with these drones is their power requirements. The batteries don't last very long. So in order to have an autonomous fleet, which can operate at farm scales or large scales, we need to have distributed power charging stations throughout the farm. You can leverage power lines or distributed stations, solar power stations, and in conjunction with designing new rapidly recharging battery technology. And so we have folks who are experts in these areas working on the project to make this a reality. Finally, we need to look at different kinds of communication solutions specific to the farm. Typically the farms are in rural areas with very poor or non-existing broadband coverage. So we need to develop some new multi-scale communication techniques for these typical cases, right? So you can have at the sensor level, low power wireless communication, like I talked about earlier. Now, then we want to also have machine-to-machine communications. So you can see here, so the combine and tractors talking together. And then we also need to have multiple input, multiple output types of communications where we can have, say, the drones talking to each other and sending data back and forth to increase the range of data transmission and also the rates to get it to the cloud. And then finally, we'll have multi-hop and distributed backhaul touch communication where we can have multiple drones or multiple autonomous agents communicating and processing different parts of the data. So observing from overhead or fusing data to come up and then using that information to kind of plan your path accordingly and then close the loop back as well. And so these are kind of the technologies which are going to work in conjunction with Thrust 2 and Thrust 3 and we're merging all this data together to make the appropriate decisions as well. And finally, our decision ag interventions, right? This is kind of the heart of it, right? So once we have all this information, what do we do with it? So we want to use data-driven models. So we have all this data we're going to be pulling from the field, from these sensors. But we also want to, constrain that with biophysical models to make sure that they make sense. So we want to do this fusion of the data-driven models and biophysical models, and then figure out, okay, what is the best data that we need in order to get the best model. So then we can employ our autonomous systems in order to get that sense of data that we need in order to get the best models. Then once we have those models, we have to merge the heterogeneous data together along with the biophysically constrained machine learning to get models of the farm. And if we have models of the farm, then we can make the appropriate decisions. All right, so we want to then kind of bridge this machine learning models and control models and uncertainty reduction by fusing the different data together and to make the invisible visible, or understand where these things that we don't know, which aren't very apparent, look at the data and kind of figure out what's going on. And then in conjunction with that, look at the economic analysis, right? So if we want to employ this, what is the impact going to be? What can my yield rate be? What are the impact if I make this decision? Is it going to be a better decision in the long haul? And then transfer that out to the field. So in order to implement this, we have lots of really nice facilities across all the different partner sites. Each of the individual PIs have their own individual labs, which has great equipment in them. But we also have shared facilities, which we can use to fabricate the sensors, test our robots, and process all the computational backbone that we need. And we have really great facilities at our research facilities, are the farms, and are also extension campuses. So we have control facilities here at Purdue. We have plot scale test beds and also farm scale test beds, both at Purdue and University of Florida and UC Merced, that we're going to use in order to push this research out. And then finally, we're really going to rely on our partners as well, industry, government, innovation partners, and also our end users in order to help guide us to our various projects, and also help leverage other resources that they have and kind of connect them together. So we have advisory boards set up, we'll have routine meetings with them. They can help give us insights and then direct our projects, and then also close the loop and maybe help us translate this research out into the field as well. So this is an example of some of the people we have signed up so far, our industry partners, and we're always open to new partners. And we have about 5 or 6 other companies we're currently talking with now, hopefully we'll sign up soon as well. And so I just wanted to give a quick project example for the center that we've worked on in the past years. This is joint work with Ayman Habib and Mitch Teenstra, and civil engineering, and also a Department of Agronomy here at Purdue. And this is on the development of agricultural robotic platform for in-row and under canopy crop monitoring and assessment. And so we know that remote sensing-based phenotyping from space and airborne systems and also wheel-based platforms has proven to be a very efficient method to capture plant traits. But there are certain things that you can't get with some of these machines. And usually that is due to their viewpoint, how far away they are, some of the resolutions of the sensors, and also the size and weight of the actual platforms themselves. So for example, this is the Purdue Pheno Rover, which is a really great platform to have. Has very high geometric resolution, but some downsides, it has limited temporal resolution because it is very heavy. So if the soil is a little bit wet, you can't deploy it that day or that week until it dries out, because you want to compact the soil. And also for some certain traits that you want to measure, it doesn't really have the best viewing angle. So the goal of this project is to develop and evaluate a small scale agricultural robotic platform that we can use for a close range monitoring and assessment of corn, particularly throughout the growing cycle. And so this is the AgBot robot platform that we developed. It's small, it's about 12 inches by 9 inches in footprint, and only weighs 6 pounds. So you can see it here driving through this wet soil. It's able to do that very easily. It's something that Pheno Rover cannot do. It has a multitude of sensors. So it has an RGB camera on the front. It has a LiDAR scanner. It also has a first-person view camera for teleoperation. It has something that's also called as a tracking camera, which helps with this in navigation, and a couple different computers. So one little computer controls the motors and the raw sensor data. We have an upboard computer, which does the main processing power for real-time image processing. And then we have a Raspberry Pi computer, which does acts as a peripheral and can communicate to a ground station and receive commands from the user that way. And so with this platform, what we want to do is to be able to come up with some geo-referenced and time-tagged point cloud data and RGB images. So if you have a GNS system or a global navigation satellite system or a GPS system, and you can add that to inertial navigation system on the robot, then you can get a time-stamped trajectory of the robot with time, position, orientation. So if you have that and you can merge that with your LiDAR data, then you can construct a 3D point cloud in a global frame, all registered together. And so that's what this little flow chart here works, and that's how you can do that. The problem is, a lot of times you may not have a very good GNS signal, or you may not have one at all. And so that's going to mess up your pipeline. And so instead of, if you don't have that, you need to estimate where you are. And so you can do that. We're using our onboard tracking camera along with sensor fusion in order to do that. So we're going to kind of replace this box with our tracking camera to give our visual odometry along with our other sensor information in order to figure out to replace that lost signal. And so in both cases, the accuracy of the 3D point cloud that you get from your LiDAR data depends on how accurate your timestamps are and your trajectory is estimated. So the better you can do this, the better data you can get. And so in order to do this, we need to map, do a very nice calibration and mapping between the coordinate frames of the different sensors on the robot. And I'm not going to talk about those details here. I'll just say once we go through the process and the system is calibrated, we did a bunch of tests to see how well it did versus our ground truth. And so here we did some tests at our controlled environmental phenotyping facility here at Purdue, where we lined up some corn in some potted plants in 2 rows. And we drove through with the robot, and you can see an example of the RGB image and the LiDAR scan. We're able to then extract both the height of the overall plants and also the height of the ears, and compare it to our ground truth. And we're able to get very nice results here that compare to the ground truth. So then once we did the indoor tests, we moved to some outdoor tests at our acre facility. And as you know, this has a lot of unpredictable factors when you're outside on the field, right? You have wind to deal with, you have variable lighting conditions. Under the canopy, we have uneven terrain, and we have obstacles. And so this is an example of some of the scans that we're able to take using the robot here. And you can see we're able to estimate the row width and the height with our system, calibrated system, very accurately compared to the ground truth. And then to see how well that we could get our georeference time tag data, you can see here, we're able to have the RGB image on the left and then the point cloud data on the right. And so what we can do is we can click on this image of the ear here, and then it can automatically register itself with the depth image. And then we can pull out the height of the ear right from this image of about 0.9 meters. Conversely, we can also click on a feature that we see inside this image here, get that information, and figure out where it is from the RGB data on the left. And so this kind of showed that we're able to accurately get the system calibrated in order to get this nice georeference time tag data. So this is an example, a proof of concept of this platform that we can use for precision ag applications, right? So it's small enough to go in between the rows, under the canopy. It's lightweight, and it can accommodate when we run out of this GNS types of signals. We're accurate to about a few centimeters, which kind of shows the accuracy of the sensor calibration. Because now where we're going in the future now is to try to make this a little bit more autonomous, a little bit more rugged. So we have a new platform which we're developing, and we're going to also add a robotic arm onto this, and not only do our sensing with our LiDAR and our cameras, but also do some sampling of the corn leaves. And so we're going to add a leaf sampling end effector to this robot hand, along with vision-based control, and try to make this more fully autonomous in the future. So that's just an example of one of the projects that we're doing here in the IoT for Ag ERC system, ERC center. We have about, 25 projects launched here in this first year. And then every year they kind of get reviewed by the board and advisory board to kind of see what they can continue and also to pivot them. So in the next 10 years, we're hoping that we can get these IoT for Ag integrated systems out and deployed so that we can have a transformative effect in the environment, really increase these types of transdisciplinary collaborations, educate the workforce, and really get more crop for every drop of water and joule of energy that's there in order to try to realize this $47 billion per year increase in crop market value in the U.S. that has been projected. And so I'll stop there, and I'll turn it over to John.
Well, let me ask a quick question here,
Sure.
Dave, before we go to John. So that was really neat seeing that little robot there in that wet soil. Boy, you could tell that was wet because it was shiny on top, and anything any bigger, even an ATV, would have made a mess out of that field. So, but a quick question, and this could be for John too, is that we've been talking about this connected farm for a number of years, and that's really what I think what you're all about. What do you see as the biggest impediment to making this all happen, where all the machinery talks and they know what each one is doing and they can make the best decision in real time and all that?
Sure. I think one issue is everything is talking different languages right now. So every type of manufacturer has their own protocol and way of doing things, and it's not as open as we would like. And so actually Dennis has a center who's kind of working on this as well, the Oat Center. And we actually have a lot of synergies there with the Oat Center. And so we're hoping to kind of work together with them. And we're going to deploy some of their IsoBlue technology on our drones and our vehicles, and hopefully use that as a way to kind of get that so everyone's talking the same language. And then the communications is the other part of it. So we have a whole thrust on communications, making sure we have that connectivity throughout the field in order to make that happen.
So still some significant issues in regards to compatibility and different formats and standards and all that kind of stuff.
Exactly.
Wanted to mention that Dennis Buckmaster has posted the project's website in the chat if you hadn't seen that, and you can keep up with it. And so Dr. Evans, John, I guess you're next in the queue, and so looking forward to hearing what you have to say. So take it away.
Thank you, Bruce. So let me see. All right, so thanks for having me today. Today I'm going to be talking about a project we did with John Deere around the development of a vehicle automated unloading system. So as most of you probably know, harvesting is a very complex operation. And one of the things that really drives efficiency is how you can get grain out of the field. And so we want to be able to unload on the go as much as possible. And for those of you who don't know, unloading on the go is when you don't actually stop harvesting ever. You unload grain from the harvester to the grain cart while in motion, while still harvesting. And that's a challenge, especially on edge cases where you're doing in turns or inclement weather. And so one of the technologies that John Deere introduced to help with that was machine sync. So basically the way machine sync works is it's machine-to-machine communication, and it lets the combine operator control the tractor's relative position. So now instead of having to be in constant communication with the tractor, the combine operator can actually command where it is and fill the cart himself. Well, that's great. He's still trying to do all the necessary operations in terms of harvesting. So he's got a lot going on, and it's very stressful, and it's hard to do, like I said, in some of those edge cases. So what ends up happening more often than it should is they end up stopping to unload because they don't want to spill grain and they're not going to risk it. And so that was kind of the motivation behind this project, is we want we want to make it where the combine operator and the grain cart operator don't have to think about this operation at all. And so when we started thinking about it and came up with this high-level system architecture that you see here. So we have our auto unload controller box, which really is dependent on four main things. Some user inputs around things like potentially cart geometry, definitely fill strategy. So how we want to fill the cart, whether we start at the back and move to the front, or start at the front, move to the back, things like that. And then we really need to know what the current level of the cart fill is, as well as the tractor dynamics. So we started out with the tractor dynamics piece, which is basically how machine sync works and how we can leverage it in our autonomous control. And so where we actually started was doing a lot of experimental system ID. And so we went out and ran machine sync with the tractor and combine, and did quite a bit of testing over a lot of months. And the way we ended up collecting the data and processing it was through a rapid prototyping system we put in to collect CAN bus data from the combine and from the tractor. And we were able to synchronize the data over a wireless CAN bridge from the tractor. So we got all the data time synchronous, and we could see what happened when we sent a command from the combine to the tractor and how it actually physically reacted. And so we developed this hardware processing pipeline to collect and process all the data. And essentially the way it worked was, like I said, we had all of the data synchronized. And so we know when we commanded a nudge, and then we could also, using the GPS data, watch how the tractor reacted to the nudge. So you can see in the plot here, a nudge up means that we nudged the tractor forward relative to the combine, and a nudge down means we nudged it backwards relative to the combine. So during the testing, we went through and did a ton of these nudges at different distances to see how the tractor would react. And essentially, we'd nudge it up, wait for, watch the step response, so wait for it to settle, and then nudge it back down to the home position, wait for that to settle, and continue this process for a lot of different configurations. And once we had all the data in, we were able to normalize it and create the transfer function that represented what happened for each nudge. And so here's an example of the plant 2 nudge, which I'll talk about in a second, which is over 1 meter and at 4 miles an hour. And so this is how the tractor reacted to that command from the combine. So like I said, we did a lot of different combinations because we were curious what the impact of different inputs would have. And so one of the things we thought would likely have a big input was the fill level of the cart. So this cart was a 1,000 bushel grain cart. It could weigh up to 60,000 pounds. And we thought that might change the way that the tractor was able to react to the input from the combine. We're also curious what impact speed had on it. So we initially tested from 2 to 6 miles an hour, and we ended up doing some higher speed testing later. And then we tested from nudges ranging from about 6 inches all the way up to 10 feet to see how the size of the commanded nudge impacted the system. And what we found out was actually somewhat surprising. The only thing that seemed to matter was the size of the nudge that was commanded. It didn't matter which direction we were commanding the nudge, so whether we wanted the tractor to move forward or backwards, which was a little surprising. I would have thought it could have slowed down faster than it could have accelerated. It didn't matter the speed of the vehicles, so it reacted the same way at between 2 and 6 miles an hour. Or even more surprising was the amount of grain. So with no grain in the cart or 60,000 pounds in the cart, it didn't seem to matter for the system at these horsepower ranges. So in total, we went through and did about 280 nudges for each vehicle combination. And we tested 3 different tractors with varying horsepowers and transmissions. So like I said, this was in collaboration with John Deere. They gave us this S790 combine with machine sync. We had the Agronomy Farms 8245R, which is 245 horsepower, with a power shift transmission. We had a loaner tractor, which is 8R340, which had an IVT or infinite variable transmission. And then we rented a 9570 to see the high horsepower or the effective high horsepower with a power shift. So each of those, we did about 280 commands for, like I said, for each. And we're able to figure out those transfer functions. So once we knew how the tractors were going to react to a given command, we could start doing some initial system design for the autonomous side of things. And so we basically added in, for the first year, we added in a, obviously the auto unload controller, and then for the, with our same setup that consisted of the rapid prototyping system that could collect, could synchronize the CAN data from the combine and tractor. Instead of having a perception system in the loop, however, for this first testing, we just used a human. So essentially, the way that worked was the human indicated whether or not the current section of the grain cart was full, and then the auto unload controller handled the direction of the nudge. So it told the tractor which way to go, and it also handled whether or not the combine auger was on or off. So we'll see if this plays. So hopefully everyone can see the video. This is our grad student Ziping, and he is acting as our perception system. So essentially all he's doing is indicating that the current section is full. And this was a front to back with a back to front top off. So they left it a little empty or not quite full. The system knows which way to go. And when it gets to the back, it knows it's at the back and starts moving forward. And you'll see as it gets to the front, it knows the geometry of the cart. It knows it can't go anymore. So instead of, once he said that last section was full, it went ahead and shut the auger off to avoid any spillage. There was also a, there's basically a boundary or a safety zone around the edge of the grain cart. So if something had happened with the tractor and the auger went outside of that safety zone, essentially the auger would automatically shut off. So that was our first pass with the autonomous system. And then the next thing we needed to do was, our last piece of the puzzle was adding in the perception systems. So obviously we wanted to take the human out of the loop, which was the whole point of this, and let the combine and tractor complete the unload autonomously. Now, unfortunately, this is the part I don't get to talk about yet. We are working on submitting patents for this. So hopefully, and I was hoping by going later in the series that some of this stuff would have been cleared and we could talk about it. But what we can talk about is the grain fill model. So this we've got a patent submitted for. And essentially the purpose of the grain fill model is, we know that in certain conditions, it doesn't matter what perception system you have. It could be a LiDAR, it could be RGB, it could be a human. You're not going to be able to see the grain pile. And so this video is a great example of that. You know, sometimes these crops get dusty and there's just nothing we're going to be able to do to actually see the surface of the grain. So the motivation was to, if we could build a grain fill model that knew the auger flow rate and the location from GPS, we could have a relative idea of what the current fill level in the cart was. And if it's low or not at really high risk of spillage, then we could continue to unload and kind of improve the robustness of the system. Because like I said, there's likely going to be at least one time during most unloads where we're not going to be able to see the surface of the grain. So this model was created by one of our students, Ziping, and it's really, really cool. It uses a constant angle of repose constraint to model the surface of the grain as a cone. And then it actually calculates a flow region in 3D space. So as the auger moves relative to the pile, it calculates where that grain can actually flow, and that informs the piling. And then there's also a filter that lets us account for jostling. So as these carts are moving around the field, they're shaking, that actually lowers the angle of repose of the grain. And so we can account for that as well. So there's going to be a lot going on in this slide. Once I click through it, you'll see these three plots come to life at once. The plot in the bottom left-hand corner is kind of a 3D representation of the grain fill. The plot in the bottom right is kind of a same thing, but with just kind of a topographic representation. And then in the top right is the spill estimation. So as I hit play, these are actually flipped. So, or the bottom two are actually flipped. So if you notice in the bottom left, you'll see when it gets to the top, you're going to see some red bars that appear right now. And that's actually where the model thinks you're going to spill. And then it actually starts to account for that spill. So I'll run that again so you can see it. And like I said, the two figures on the bottom are actually inverse right now. So apologize for that. But there you can see the spill where it happens. You can see that we're now accounting for spill, and we're continuing on. So once we had this awesome model, we needed to go and figure out if it actually worked. And so the way we did that was actually going out and bolting a LiDAR unit on the side of our grain cart. We were able to image the inside of the grain cart as it was filling. We'd stop periodically to make sure we were seeing the grain and not dust. And we wanted to just verify that our grain fill model lined up with what was happening in the real world. And we also really wanted to verify our spill detection, because that was really the most important part of the grain fill model. We wanted to know or have a good estimation of when we thought we were going to spill, even if we can't see the surface of the grain. So to be able to do that, you got to go spill some grain in the name of science. So this was this is out at the Purdue agronomy farm where we did all of our testing. We essentially went through the unload until it got full, and then continued to go until we got spillage so that we could see if our grain fill model was actually going to be able to predict that. So there we go. And then, like everything in life, it's much more complicated than you think. So we needed to be able to compare the surface that our LiDAR was giving us with our model, and that is not trivial. So our students went through and did an excellent job of actually processing this data. So you can see that the grain cart, picture of the actual picture of the grain cart, you can see all the things like the tart bows and the internal bracing that really get in the way of the LiDAR. And so we needed to be able to actually process that and filter that data out. So they went through and created an algorithm that identified where those brackets and tart straps were, and figured out what was causing the occlusion. So you can see here we're in the unprocessed height map, we're actually missing data. That data in white is missing, and that's because it's occluded by the tart strap. And then actually averaging to get rid of the effective C in the wall. So they were able to go through and do that, and basically do some interpolation to do the filling so that they could get a complete service. So here's an example of the actual data we took and it filling the grain cart. So now that we could get that, we could go through and actually do our comparison. So the first thing we did was a comparison of no calibration. So just comparing what happened with the grain fill model running, and then comparing that to the real world data. And so if I push play, you can see here's basically those overlaid with the error. And our max error was about 0.3 meters, which is fairly good for this operation. And as you can see, it occurs right next to the wall. And that's actually from an averaging error or filter that could be updated to even account for that more. So really positive results. And so this was throughout a whole fill that, we were only off 0.3 meters across the entire fill. Another strategy we wanted to look at was one that would likely be more realistic to deploy on the production scenario. So this would be a sensor fusion model where you have the perception sensor that's seeing the pile and actually updating the grain fill model in real time. And then if the perception sensor loses the pile, the grain fill model is still running and you can still get an estimate. So I went through and did that. And basically it's updating that grain fill model every LiDAR frame, which in this case was about every 80 bushels. And so you can see the comparison there. And so this is as it was filling. And you can see they look remarkably similar, which is excellent. And if we switch to the error plot, Similar to the last one, we get very low error between the actual and predicted by the grain fill. The range is similar to the uncalibrated version, but the frequency of that error is less. You can see that we don't have the error around the edges like we did with the uncalibrated one. So I would love to be able to share with you how we implemented this, because we did actually get it implemented, and hopefully in a future presentation I'll be able to do that once this clears John Deere's internal review. We've got 4 papers there now under review, and so hopefully when those are released, we can tell you what we did with the perception system and augmenting this grain fill model. I'd be remiss if I didn't thank our team. We've had a great team here at Purdue. This was led by Greg Shaver over in ME, as well as by myself and Tony Vine in agronomy, along with Dan DeLaurentis. We had a lot of great students working on this, as well as other research scientists. And with that, I say thank you, and we can open up for questions.
Okay, I have a question or two up my sleeve, but I would much rather have one of the people that are listening in today participating. So as we always do, open up your mic, unmute, and ask your question if you have one. Otherwise, I'm going to stick mine in there. So, and John, I have to say, I love how you use a very casual term like nudge. You're working on such detailed information, and then just found that humorous.
That is the official John Deere term.
Cool. Yeah. Okay. In terms of positioning and in terms of monitoring the fill, which both have to happen. Who has a question? Okay. Well, guess people are a little shy today, so let me ask my question. I guess a couple questions here. Are there any of these systems, autonomous systems? I know of some companies that are doing this. How many of these are already working on commercial farms in the U.S.?
So in terms of the actual unloading, my understanding is 0. I know Ag Leader has CartAce, which essentially shares the AB line, similar to machine sync, but it doesn't allow you to control the vehicle. So that would just help the cart operator get lined up, but he's still in control. I know how Smart Ag, who is now owned by Raven, initially came out with a system, but my understanding was theirs was autonomous in terms of the cart. There was no driver in the cart, and the cart could get to the combine. But my understanding was that actually the fill itself wasn't necessarily autonomous. The combine operator had to actually nudge them forward, but there was no one in the cart, or there's no one in that cart.
Right.
In that case. So to my knowledge, there's no fully autonomous solution currently production available.
Okay. Yeah, and I saw that Smart Ag system at the Farm Progress Show a couple of years ago there at Decatur, and that was pretty neat to see that. So, there's a question in the queue that it's kind of related to the question that I had too. Is related to current farmers, the economics of this. What might be the price point of a totally autonomous grain cart system? Do you have any inkling on that? I mean, because what you're basically replacing is grandpa out there maybe driving the grain cart, and the rest of the family managing everything else.
So
because you typically don't put your most skilled person in the grain cart, do you? It's been my observation.
Not usually.
Yeah.
That's a great question. I think I don't have specific numbers. It's going to come down to your efficiency gains, though. So for efficiency gains and labor savings. So for big farms that have ample labor that's good and qualified, it might not be that attractive. For farms where they're struggling to find good labor, and they're having to drive to the field edge to unload at a grain cart and wait for the trucker to actually unload the grain cart to the truck. That's where you could see some significant efficiency savings, which are really hard, easy to quantify in terms of what you're saving that day, harder to quantify in terms of, that one day where you're able to get the field done before the windstorm comes through, as opposed to getting it half done and losing a bunch of corn that way. I'm sure John Deere has better numbers on that, or estimates. And I know that's something that they've been thinking about is how does this become commercially available? And that's one of the issues with some of these perception sensors is right now they're at a pretty high price point. And that's coming down constantly with all the automation going on in the on-road sector. So short answer is I don't know what the exact savings are, but I do know that this is something that in the future will hopefully be fairly economical to implement.
Question from Elaine here in the queue. Are there any dairy farms that grow their own feed that are looking at these types of solutions? And so maybe that's a silage kind of a question, I suppose.
Yeah, so that's actually a great question. So this type of system actually exists in the silage world. So this is kind of a modification. So I think it's autofill is what John Deere calls it. Kloss has their own version. And this is where this technology started. So they're actually, because in silage, there's no capacity on the silage chopper. So they're always unloading into a truck. And so I think it's been for a couple of years now, John Deere and Kloss both have this where they actually they're looking at the truck, figuring out the edge of it, and then using they're actuating the spout itself to automatically fill the silage wagons. So that's a great question. Yeah, that technology is actually commercially available right now. And I should have mentioned that earlier.
I mean, I think the name of the game, whether it's grain or fresh plant material, is that you got to keep that harvester moving for the economics, because you've got really expensive equipment that you can't have sitting. Isn't that right?
Exactly. So, I mean, that combine we had there was well over $500,000.
Yeah.
Some of the new bigger ones are pushing 800,000.
So I got a question for Dave. Dave thought he was maybe off the hook here, but because you were looking relaxed there, Dave, but I want to hit you with a question.
Sure. I had one comment on the economics. I can
good.
Add as well. So there's this new idea, you may have heard of it, it's called farming as a service. And so some of these companies with these robots have the idea like you will hire them for 2 weeks to do your planting. And so they'll bring the robots, they'll go out, they'll do it really fast, efficiency. And then you hire them back to do your harvest or weeding or something like that. So that is one kind of business model that is out there. And so maybe that could be the same thing with the combines, right? You don't have to buy this huge piece of equipment. You would just buy this service, or people will give you your data. And so it could be like a monthly subscription or something. But that's one approach that people are thinking about with these.
Yeah, and I can't think of the name of the company, but I know that they're working
in too.
Oh yeah, they've got in northern Indiana. I know they're working in west central Iowa. They're working where I used to work. So and they're using smaller tractors, from what I understand, for their planting, like Kubota's smaller one. So, and my question for you, Dave, we've just had this pipeline situation here, and how vulnerable would we be in ag to someone, getting into turning on the irrigation when they shouldn't be, or, telling the tractor to start planting when it shouldn't be?
Yeah, that's a great question, right? I mean, security is always an issue with these things. And there's a component to it too. So on the communications thrust side, not only do you want to make the communications happen, but make it secure. And so, that is a big component to it. And there are people who are working on that. That's not my particular area of expertise, but yeah, that's same thing with autonomous vehicles and cars, right? Everything is connected.
Right.
How do you make sure that's secure, right? So it's all kind of the same kind of issue there and challenge.
So I don't see any additional questions. And John, thanks for putting that in the queue, the link to the active fill control. Appreciate that. Do either of you have any final parting comments? And if not, we can just call it a day, and we can call it a whole series here today too. So anyway, thanks everyone for your participation today, and we'll let you know when we fire these back up again. And this was one to end up on, some really interesting work that's being done here. So thanks again. We'll end it for today.
Thank you.
Yeah, thank you.